So here we have a representation, just to reinforce. The Bohr model, orbits, no more. Quantum model, which deals with orbitals. Orbitals tell us the probability of finding an electron. That's what we see here. That's what these dots represent. You see more dots here? More dots here represents a higher probability. Fewer dots out here represents a lower probability. This is a probability map, electron density map. These are what the orbitals look like. These are the S, here are the p orbitals, here are the d orbitals. Here it's going from 1s to 2s to 3s, higher energy, bigger orbitals. There are other things that are different too, but we aren't going to get into it. So the p's would do the same. Pauli exclusion principle we'll talk about a little bit later. But basically, from here, we're going to move to our supplement. Near the beginning of the supplement, is a chapter called Quantum. So let's take a look there. This is right after the nomenclature. Nomenclature we get. It's called Quantum Numbers and Electronic Structures, Quantum 1. Here it talks about the these three letters, N, L, and M. These come from the Schrodinger equation. So N is the principal quantum number. These are allowed, N 1, 2, 3, 4, all the way to infinity. L is called the angular momentum, or azimuthal quantum number. Tells us the shape, pretty much. 0, 1, 2, 3 to max. This is max allowed. And so it takes on all these values up to the max and minus 1. And then M. M is called the magnetic quantum number, and that tells us the orientation. It goes from minus L to plus L, going through 0. All values. And so what does this generate? This generates a map, and the map is called the energy level, orbital energy level diagram. This is here a map showing all the allowed states, the allowed energies for the electron, states, the shapes. Actually, one's missing here. Take a look at the gaps. Do you see where's the biggest gap? The biggest gap is going to be between the 1s and the 2s. There's a small gap between the 2s, 2p's, and a bigger gap between n equals 2 to n equals 3, n equals 4. But as we get higher and higher, the gaps become smaller and smaller as things start to converge. So this is pretty much the map of the allowed energies of the electron in an atom. It's not a complete map because to be a complete map, how many lines would there be? How many lines would there be? How many allowed orbitals are there for an atom? Infinite. But there are some things you could see here. And that is, the way it's organized is like this. The first column is L equals what? 0. Then we go to L equals 1. When L equals 1, M can be minus 1, 0, plus 1. Minus 1, 0, plus 1. Those are the allowed M values. Then we go to L equals 2. Minus 2, minus 1, 0, plus 1, plus 2. Patterns we see. This diagram is not complete because when n equals 5, how many allowed L values are there? And so when n equals 5, L equals 0 is allowed. Therefore, when L equals 0, M is equal to 0. When n is equal to 5, L equals 1 is allowed. If L equals 1 is allowed, then we have M equals minus 1, 0, plus 1. So we got 3 p orbitals. When n equals 5, then L equals 2 is allowed. We got here, minus 2, minus 1, 0, plus 1, plus 2. That gives us 5 M values for each L. When n equals 5, then L equals 3 is allowed. How many orbitals are there? There's minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. There are 7 orbitals. That's for L equals 3. But there's one L value missing. What is that? And so when n equals 5, L can be 0, 1, 2, up to a maximum L value of what? 4. So what's missing is L equals 4. And so those would be the 5F, those would be the 5G orbitals. The 5G orbitals aren't shown here. How many orbitals are there in the 5G orbitals? And so if I were to draw the 5G orbitals, how many lines would I have to draw? So 5G, G means L equals 4. If L equals 4, then M is going to equal minus 4, minus 3, minus 2, minus 1, 0. What's the rest? 1, 2, 3, 4. So count them. There's 1, 2, 3, 4, 5, 6, 7. Actually, did I get that right? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 orbitals. And so I'd have to draw 9 lines for the 5G. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I call those the 5G. And each of these would have a distinct shape. The only difference would be the orientation. 3-dimensional space.
And that 5G, does that come from the 7th level? Where you're talking about?
Well,
Or is that something?
we'll talk about that in just a second. But the 5G, it comes from the 5th energy level. We'd call it the 5th energy level. Let me tell you, it's a little bit confusing here. But let me tell you how many we can fit. There are always going to be 2L plus 1 orbitals per subshell. So for example, the next one would be L equals 5, which we would call, after G comes, what? H. And so, for example, do the 5H orbitals, are those allowed or forbidden? Allowed? Are 5H orbitals allowed? 5H orbitals are forbidden. And the reason that 5H orbitals are forbidden is because L equals 5. If N equals 5, can L also equal 5? No, because it exceeds the max. The max L value is equal to N minus 1. And so the max L value is 5 minus 1 is 4. And so the 5H orbitals are forbidden. But the 5G orbitals are allowed. Are 6H orbitals allowed or forbidden? Are 6H orbitals allowed or forbidden? Six H orbitals are allowed. How many orbitals are there? Okay, you could do, how many orbitals are there? Well, okay, that means L equals 5. If L equals 5, how many orbitals are there? 11. There are going to be 11 orbitals. what are they? They're -5, -4, -3. We count them. Or we fill out the pattern. It's 2L plus 1. Now, do you see how the orbitals are getting mixed up? When look how mixed up these orbitals are. You know, we'd like to go 5s, 5p, but it doesn't go like that. It goes 5s, 4d, 5p. And so all the orbitals start getting mixed up. Well, in order to keep those in the proper order, we follow that pattern that I showed you earlier. And that pattern that I showed you earlier is how the orbitals are going to increase in energy. So what was that pattern? The pattern that I showed you earlier is like this. And so the way I can generate that, because look how mixed up it goes. If we go it doesn't go in order. It goes 1s, 2s, 2p, okay, 3s, 3p. But rather than going to 3d, it goes to 4s, and then 3d, and then 4p. And then 5s, 4d, 5p, 6s, 5d, no, 6s, 4f, 5d. Do you see that? And so that ordering we can get from this. 2s, 2p, 3s, 3p, 3p. That ordering we can get from this. Now, that means that means it becomes weird in the way that the energy levels, you know, we were talking about the energy levels, like the first energy level, n equals 1, is the lowest energy. And then the next energy level is n equals 2. And so you're on the first floor, and then you're on the second floor. Then the next one would be 3. But something screws up happens when we go to the third energy level, this 4s pops in there. This 4s is actually lower in energy than that 3d. So things start to get mixed up. And so as far as the n, of course, the higher the n, the higher the energy. And so n equals 1, L equals 0. N equals 2, L equals 0, L equals 1. If L equals 1, we have -1, 0, plus 1. N equals 3, L equals 0, it's S. L equals 1, that's a P. L equals 2. Could I have a 3f orbital, or 3f orbitals allowed? No, 3f orbitals would be forbidden because that's L equals 3. When n equals 4, I have the L0, L1, L2, L3. When n equals 5, I have L0, L1, L2, L3. What's missing? I have the 5f, and then what's missing, the next one should be the 5g. And so this is kind of cut off at the top here. It's cut off. There's a reason it's cut off. I'll tell you when it's cut off. But you know, they aren't showing all the orbitals. There's more. When n, let me ask you this: when n equals 6, how many L values, how many sublevels do I have? When n equals 6, I should have 6 because we start at 0. So when n equals 6, it's 0 is allowed, 1 is allowed, 2 is allowed, 3 is allowed, 4 is allowed, 5 is allowed. That's 6. So for every n, there's 6 sublevels. So n equals 1, 1 sublevel. N equals 2, 2 sublevels, S and P. N equals 3, 3 sublevels, S, P, D. N equals 4, 4 sublevels, S, P, D, F. N equals 5, 5 sublevels, S, P, D, F, and G. N equals 6, how many sublevels are there? 6. S, P, D, it's not drawn here, but what would be after D? F, G, and H. And so this, by using this pattern, we could figure out all the orbitals all the way up to n equals infinity. It's just a simple mathematical pattern we do. Now, the orbitals are all mixed up, and so based on this, how the energies are, this is the way we visualize this. The way we visualize this is in terms of something called periods or shells. I like to call them shells. A shell is a group of closely spaced orbitals in terms of energy. And so in the first shell, we only have one orbital, so one s orbital. In the second shell, this group of orbitals has similar energy, so the 2s and the 2p, there are two sublevels in the second shell, or two subshells in the second shell, the s subshell and the p subshell. In the third shell, we have two subshells. No, in the third shell, we only have, in the third shell, we should have three, right? We should have three subshells or three sublevels, but we only have two. Why? Because the 3D are a bit higher in energy. And so the 3D aren't part of the third shell. In the third shell, we only have the 3s and the 3p, and it turns out that the 3D get promoted to the next shell. That would be the fourth shell. In the fourth shell, we have the 4s, the 4p, and the 3d, so it starts to get mixed up here. But these set of orbitals are, in terms of energy, very closely spaced. So it goes 4s, and then the next higher energy orbital would be 3d, and then the 4p. You should be able to draw the orbital energy level diagram to the 4p, and you should be able to write the numbers here. Then we'll stop. In the fifth shell, we have these, the 5s, the 4d, and the 5p, in the fifth shell. In the sixth shell, we have these. And so this is more useful. We have shells of orbitals. They're more useful than the energy levels.
So you want us to memorize that way, or
Well, okay, we're going to go up to the 4p subshell. And so the way I would do it is like this. I'd say the first line here is the lowest energy. That would be the 1, 0, 0 orbital, or the 1s. 1s and 1, 0, 0 is the same. This is N, this is L, this is M, N, L, M. And so then the next one would be the 2s, which would be 2, 0, 0, N, L, M. And then in this would be the first shell here. The first shell, or first period. I'll just call it shell. In the first shell, there's only one subshell. In the second shell here, in the second shell we have the 2s and then the 3 2p's. The 3 2p's are going to be 2 1 minus 1, 2 1 0, and then 2 2 2. 2 1 2, sorry. In the third shell, we only have two subshells. In the third shell, we have the 3s, would be the 3 0 0. And then the 3p. What happened to the 3d? The 3d ended up going into the next shell. So this is 3 1 minus 1, 3 1 0, 3 1 1. And so here it's organized in terms of n and organized in terms of L. L equals 0, M equals 0. L equals 1, M equals minus 1, 0, and 1. Okay, that's the third shell. And then we go into the fourth shell. The fourth shell, you should know it up to the fourth shell. The fourth shell is going to be the 400. The 400, aka what? The 4s. And then you would think it goes to the 4p, but it does not go to the 4p. It goes to the 3d. There are 5 of these. These are the 3d. Now 3D is abstract, but if you have the numbers, it's a lot easier. What are the numbers? This would be 3. What's the next number? 3. Well, it can't be 3 0. We use that. It can't be 3 1. We already used that. So what comes after 3 1? 3 2. And so here, L equals 2. So if it's 3 2, then what are my possible M values? Well, if it's 3 2, my M values are going to be minus 2, minus 1, 0, plus 1, plus 2. That's 5. So 3 2 minus 2, 3 2 minus 1, 3 2 0, 3 2 1, 3, 2, 2. Do you see this pattern that comes up? All right, and so it goes from 4s to 3e to 4p. And this would be, what's the first line here going to be called? 4, 1, minus 1, 4, 1, 0, and 4, 1, 1. This is the fourth shell here. Well, what happened to 4D? You know where the 4D are at? In the next shell. So we're not going to deal with the 4D. The 4D are in the next, and the 4F are in the next shell. So those are higher shells. Okay, these are the orbitals. So N, L, M define the orbital. Now, where do the electrons go? The electrons go into the orbitals. So when we put electrons into orbitals, we need to know something about electrons. There's one more quantum number. These are called quantum numbers. So 3 quantum numbers define the orbital. That's kind of the address of the electron. So it's the address. We can, okay, electron's in the 5, 1, 0. Then I know exactly where that electron is, which orbital it is. It's in the 510 orbital. It's address. If I said the electron's in the 3p, then I don't know which one of the 3p's is it in. Is it in the 3, 1, minus 1, 3, 1, 0, or 3, 1, 1? And so this is the advantage of having the 3 quantum numbers. We'll know. You could get rid of that by just saying px. It's in the 3px, or the 3py, or the 3pz. You can get rid of that in computing. Okay, now the electron itself. Electrons have spin. Something called spin. And it's like a little magnet. And so you could have the North Pole up or the North Pole down. It's like a little magnet. There are 2 orientations. And so when we look at an electron, the electron can be spin up or the electron can be spin down. That is, it can have the North Pole up or the North Pole down or something like that. Depends on right-handed or left-handed. The spin, this comes from, magnetic, the magnetic part of electric. Call this spin up. We call this spin down. And we give a number code to it. And so the designation for spin is S. That's the spin quantum number. Spin up is plus 1/2. This comes from the mathematics. So this is why we have these funny numbers. Spin down is minus 1/2. There are only 2 possible spins. Spin states. So, for example, the way I'm going to write or represent electrons is by using an arrow now. And so, let's put an electron here. I'm going to put an electron here. Okay, where's that electron? That electron is in the 3, 2, minus 2 orbital, or it's in the 3d orbital. Is it spin up or spin down? We say it's spin up. And so this is plus 1/2. And so in order to define an electron in an atom, we need 4 quantum numbers. The 4 quantum numbers that we need are N, L, M, and S. N, L, M. The first 3 quantum numbers tell us which orbital. The last quantum number, S, tells us is it spin up or spin down. And so that one red electron there is defined by 4 numbers. It'd be 3, 2, minus 2, telling me which orbital it is. And then if it's spin up, I call it plus 1/2. That would be that red electron there. Okay, let's put a green electron here. What are the 4 quantum numbers for this electron here? This would be 2, 1, minus 1, and negative 1/2. And so this one would be a 2, 1, minus 1, 2, 1, minus 1, minus 1/2 electron. That would be my NLMS. And so I know exactly where that electron is, and if it's spin up or spin down, I can tell. Here's arranged in sublevels. L equals 0 at the S sublevel, L equals 1 at the P sublevel, L equals 2 at the P sublevel, L equals 3 at the F sublevel. It's arranged in sublevels in your book here. And so what we're going to do is we're going to get some practice. A lot of these atoms have a lot of electrons, so you should know this up to the 4th shell. The 4th shell would go up to the 4 P. This is not really spread out the way I like it. So we're going to go back to this one. And we're going to look at putting electrons in the orbitals here. So how many electrons does hydrogen have? Erase this. Hydrogen has 1 electron, and that 1 electron normally is in the lowest energy, either plus 1/2 or minus 1/2. It doesn't matter. Helium has 2 electrons, and normally it's in the lowest energies possible. The lowest energy possible would be this. It turns out that each orbital can hold a max of 2 electrons. Each orbital can hold a max of 2 electrons. That's given a fancy name. Do you know what that's called? That's called the Pauli exclusion principle. The Pauli exclusion principle says this: more than 2 electrons cannot occupy the same orbital in an atom. And so what we can have is we can have an empty orbital, or we can have an orbital with 1 electron, or we could have an orbital with 2 electrons. If the orbital has 2 electrons, then the spins have to be opposed. That is, they can't have the same spin. What the Pauli exclusion principle says mathematically is that this. Pauli exclusion principle says that no 2 electrons within an atom can have the same set of 4 quantum numbers. And so each electron in an atom has to have a unique set of 4 quantum numbers. And therefore, since there are only 2 spin orientations, that means plus 1/2 takes one, minus 1/2 takes the other. So I can't put another plus 1/2 and I can't put another minus 1/2. So this is, hydrogen has 1 electron, helium has 2 electrons, lithium has 3 electrons. So the 3rd electron has to go to the next orbital. The next orbital will be the 2. And so if I go to lithium, lithium has 3 electrons. I got to go up here. And I can put it spin up or spin down, it doesn't matter, but normally I just put it spin up. It's convention. So that's lithium. Beryllium has how many electrons altogether? Beryllium has 4 electrons. So where should I put the 4th? Should I put the 4th electron in the same orbital, or should I put it in a different orbital? Well, if I want the lowest energy possible, I'm going to put it in the same orbital, but I have to flip the spin because of the Pauli exclusion principle. And so what I need to do is the 4th electron is going to go here. So this would be beryllium. Beryllium is 4 electrons. And then after beryllium comes boron with 5 electrons. Where should I put the 5th electron? What orbital should it occupy? Well, the 5th electron has to be promoted to the next orbital. Now these 3 orbitals have the exact same energy, so it doesn't matter which one of these 3 I put the 5th electron in. I could put it in any one of these 3, and I could put it spin up or spin down, it doesn't matter. But, you know, I'll just pick this left one and put it spin up. Now, where should I put the 6th electron? Carbon has 6 electrons, and so the 6th electron should go in the same orbital or in a different orbital. Normally put it in the same orbital, but there's something called Hund's rule, which is not talked about in the book. Hund's rule says this: when we're filling energetically degenerate orbitals, these 3 orbitals have the exact same energy, then it's lower in energy to fill these one at a time. And so once I put 1 electron there, I want to put the next electron in the next orbital over here, or in this orbital. It doesn't matter. These are orthogonal to each other. And I should put these parallel spin. That is, the spins should not be opposed like here, but the spin should be oriented in the same direction. So if I put the first one spin up, the second one should be spin up. It's Hund's rule. And so Hund's rule says fill energetically degenerate orbitals one at a time with parallel spin. Right down here. So these are important. Poly is important. Poly says max capacity 2 electrons, opposing spin. Hund's says fill degenerate. Degenerate just means the same energy. Degenerate orbitals one at a time or singly with parallel spin. So that's what I did. Carbon has 6 electrons. The nitrogen has 7 electrons. So where should the 7th electron go for nitrogen? Yeah, over here. And the spin up or down? Yeah, spin up. Nitrogen would be like this. That would be nitrogen. Now, this is the most descriptive way to represent. You know, nitrogen has 2, 4, 6, 7 electrons, and where are the electrons? These electrons are going to occupy these orbitals in the nitrogen atom. That's where the electrons are. But it takes up a lot of room, and so one thing that's often done is people do this. For example, nitrogen, they'll write something called the electron configuration. The electron configuration takes this diagram and compress it into one line. We lose some information. And so nitrogen's electron configuration would be 1s orbital with 2 electrons, so we call it 1s2. And then 2s orbital with 2 electrons. And then a 2p orbital with a total of, and the 2p set of orbitals will have a total of 3 electrons. And so we call it 2p3, half capacity. And then 2p subshell, we can hold a max of the 6 electrons, so that would be nitrogen. This is a lot less informative than it. What was this diagram called? Orbital energy level diagram. What's this called, the shorthand? Electron configuration. So orbital energy level diagram is much more informative than electron configuration. But it takes up a lot of space. Compared to electron configuration, the advantage of electron configuration is very compact. It doesn't take up much space. Okay, after nitrogen comes oxygen. Now, what happens with oxygen is now we have to pair. It's called pairing. We have to pair it. We can pair it in any of these. We'll just pick the first one. So if I have to pair this, then I have to put opposing spin. So that would be oxygen. And then comes fluorine. Fluorine, with 9 electrons, I'm going to have to pair it. And then after fluorine comes neon. Now, neon, I'll pair it like that, but one thing about neon is it's filled shell. And so if I look at neon, I filled the first shell, and then I filled the second shell completely full. And so filling the first shell corresponds to helium. Filling the second shell corresponds to neon. Let's go to the third shell. When I go to the third shell, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've used 10 electrons, so 11 electrons would be sodium. So sodium with 11 electrons, that electron would go here. And so sodium would be a 1s2, 2s2, 2p6, 3s, 1. And then from sodium, I would go to magnesium. Magnesium would go 3s2. And then from magnesium, I go to aluminum. It would be 3s2, 3p1. And then across. And eventually, these Hund's rule says I fill these how? Singly. And so from aluminum, I would go to silicon. And then silicon to phosphorus. Once I'm at chlorine, then I'll go to argon. Argon. And so once I fill the third shell, I'm at argon here. And so the theory underlying the chemistry is based on the periodic table here. The periodic table is hydrogen, 1s1, helium, 1s2. That fills the first shell. The second shell would be the second row, the 2s and the 2p. Once I fill the 2s and the 2p holds 6 electrons. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Once I fill that whole subshell, I will be at neon. The third shell will be the third period. Start off with sodium, end up at argon. The fourth shell would consist of the 4s, followed by the 3e, followed by the 4p. So the fourth shell would be the 4s, followed by the 3e, followed by the 4p. Once I fill that fourth shell, I'm at what element? Krypton. Yeah, filling the fourth shell. The fifth shell is weird. Actually, the fifth shell is fine. Fifth shell is fine. It goes 5s, 4d, 5p. The sixth shell is weird. When I'm at the sixth shell, it goes 6s. And there's not enough room because we have to insert the 4f in here. So it goes 6s, 4f, 5d, 6p. Since there's not enough room here, they cut it out and drop it down here. So if you look at this periodic table, do you see the double asterisk here? And so it goes 6s, and then double asterisk goes, means we drop down here to the 4f, and then we come back up here to the 5p. So it's a bit tricky here. The periodic table is not long enough to insert these, so these have to be separated out of there. And so the periodic table, the basis of the periodic table is quantum mechanics. Let's see that this would be the first row of the periodic table, the second row of the periodic table, the third row of the periodic table, the fourth row of the periodic table. So let's take a look at the electron configurations here. We should be able to name the quantum numbers for any of these electrons, which you can do, but eventually we're going to just do these electron configurations. So hydrogen 1s, so we already went through these. But what we can do here is we can use what we call novel gas electron or core abbreviations. Okay. So we have the helium core, the neon core, the argon core. The helium, this is 2 electrons, neon's 10 electrons, argon is 18 electrons, etc. And so this is what they did here. For example, sodium. We can write out the full electron configuration. It would be 1s2, fill the first period, the first row. 2s2. 2p6, 3s1. And so what we can do is we can abbreviate up to here. If we fill the first row and the second row of the periodic table, we're at neon. And so what we can do is we can write out the complete electron configuration like this, or we can write out the electron configuration like this using an abbreviation for novel gas fluoride. This is what they did here. Let's see, they wrote neon in brackets 3s1. And so the same as neon, and then they have 3s1 for that one. We're out of time. Yeah, we're out of time. The same thing with potassium. Look at it. They put argon for 4s1. So we'll look at this next.